Hi there, so my name is Jennifer Milne and today we're going to be talking about generative design for additive manufacturing. So a little bit about me. I lead product marketing here at Formlabs, but I've been here for about 8 years, so I've grown with the company to where we are today. Originally got started in the CAD/CAM industry back in 2004, working in steel fabrication. My background is mechanical engineering, but with a focus on product development and the product design process. And then at Formlabs, I've done various things, but mostly my team work on bringing new materials to market, as well as understanding different applications and workflows. So a little bit about Formlabs. I've kind of into generative design shortly. So we are primarily a hardware manufacturer, best known for desktop resin-based systems. We started Form 1 and all the way to today in 2020, but we kind of have these three flagship 3D printers, the Form 3, our large format Form 3L, and the Form 3B, which is dedicated specifically to biocompatible material. While we're focused on hardware, we also make all our own materials, and we have an expansive resin library. We have standard resins for general prototyping, as well as specialty resins. So a lot of engineering resins for more challenging applications, as well as our dental materials or biocompatible materials, and some castable resins for the jewelry industry. And our whole ethos is about making technology accessible. We were one of the first companies to take SLA 3D printing or stereolithography and create a more affordable, easy to use desktop solution. And we're excited that we've announced that we're also doing that for SLS. So SLS is a nylon powder-based system. And with the Fuse 1, we're making SLS 3D printing more affordable and accessible. So our mission is to expand access to digital fabrication and help anyone make anything. So while we're normally in the hardware world, we're also wanting to bring new content and help you with the design of products. And that's why we're going to be talking about generative design today. It's a really interesting sort of new field, and you may have sort of heard about it, be wondering how it relates to the work you're doing, and how you can take advantage of it. And certainly, as Formlabs, we have lots of customers who are pushing the boundaries of 3D printing and also pushing the boundaries of their design process. So when you think about generative design, or if you punch it into Google, you're going to see a lot of images like this. So very organic shapes, very complex geometries, lots of things made out of metal. It all looks very futuristic, and you may kind of have mentally decided it's very R&D, it's sort of coming out of research universities and things like that, and that it doesn't really relate to the more traditional work that you're doing in part design and product development. And my goal with this presentation is to sort of expand your understanding of the field of generative design and give some more relatable examples. So, you know, it may be something that you want to explore that makes sense for the work that you're doing. So here's the agenda. I'm going to do an overview of what is generative design, a bit of a definition. I'm going to talk about why there are so many brackets. There's a bit of a story behind this specific part that a lot of companies are using to showcase what their software can do. Then we're going to do a step-by-step tutorial of a generative design process using Autodesk's Fusion 360. And then I'm going to talk about why generative design and additive manufacturing are often talked about in the same breath. They're sort of two different technologies, but they play really well together, and there's a lot of benefits from one without the other. And then we have two examples. Quill is a case study about automated wheel, and it is an example of a company trying generative design for the first time. And then we're going to talk about New Balance and their work to improve midsole design with much more of a sort of long-term vision for what they want to do in a project that's been going on for several years. So a very sort of like straightforward first example of a company using our technology, and then a sort of more complex one. Cool. So what is generative design? design is a design exploration process that involves a program. So essentially, it's a design process. It's a way to generate ideas and physical product design. You start with an initial idea. There's a program, so you kind of have an understanding that there's some software in the middle, and out come a bunch of solutions. And now if we take that one step further, this program is going to generate a number of outputs that meet certain constraints. So we sort of expand this model to say there's not just a bunch of solutions, there's sort of n solutions, there's sort of an infinite solution space. And then that software, we can think of it as rule algorithms and the underlying source code. So basically it's still software, but it's important to acknowledge that there's kind of some rules about how you reach the solutions, and the source code can kind of provide the different input variables. And then where does the designer fit into this? So the designer is really there to sort of fine tune the solution space by modifying parameters, rules, or underlying code. And this is as complex as this definition is going to get. So when we put that all together, you know, normally the designer is sort of responsible for this sort of linear design process or a double diamond design process where you're sort of exploring ideas and pulling back towards a solution. Whereas here, the designer is really responsible for this whole process and this feedback loop. So the designer's role is to look at all the solutions, judge the output, and then they kind of go back in and fine tune by either you know, changing the rule algorithms, making adjustments to the sort of input problem and the input variables, and then you're going to get, you can reiterate and get a bunch of different solutions coming out. So it's not wildly different from how you may design products today, but it is much more focused on this sort of iterative feedback loop, and the designer's role is more about the logic and the definition of how you're going to reach those solutions. So again, one thing which maybe you know, holds back the adoption of this technology is if you start researching generative design, you're going to see all these awesome visualizations. You know, you're generating an infinite number of design solutions. This makes it very easy for companies to do really cool marketing where they're like, here's 100 variations of a, you know, a frame for a drone. And it can feel very heavy on the data visualization side. It can feel like it comes from this world of coding and yeah, coming up with cool motion graphics and things like that. So I want to sort of shift your perception, and I'm going to focus on Autodesk Fusion 360. So this is what it actually looks like when you spit out a bunch of solutions. It's much more organized. You get a bunch of options and you can click into those. So this is a screenshot from Autodesk Fusion 360, and we're going to stay with that for the step-by-step tutorial. And yeah, basically you can, there's a few different views, and you know, one of them is this grid view where you see all these different options, but you can also move to a scatter plot view, and here you can choose von Mises stress versus maximum displacement, and you can actually go in and click into any of those. So you'll start to see clusters of solutions within your solution space. So this is kind of where that designer's skill and experience comes into play. You know, you may have a cluster over here, and your knowledge of the end use application may make you realize, okay, we actually can only tolerate you know, 1.5 to 2 millimeters of displacement. So let's click into these ABS plastic solutions. Cool. So now I'm going to talk about this GE bracket challenge. It's going to feel like a little bit of a departure, but it's going to come back when we get to the tutorial portion. So GE, General Electric, posted this challenge on GrabCAD. GrabCAD is an online community of CAD users, people using computer-aided design. And the challenge asks them to use additive manufacturing as the basis for optimizing an existing aircraft engine bracket. So the nice thing about this challenge was they gave them all the information. It was a really well-defined problem. So here is the existing traditional bracket that they were asked to optimize. They had the full geometry for that. And then they also provided the 4 loading conditions as well as the different interfaces and mating points. So this was a really nice, well-defined, closed problem. You know, it's probably reminiscent of the kind of stuff you worked on if you were an engineer in mechanical engineering school, where it'd be a sort of classical statics or dynamics problem. So all the information was sort of available, and the challenge was to focus on how can you optimize this by removing material and making it super lightweight, giving additive manufacturing as the intended manufacturing process. So there are a bunch of solutions, and they picked the winners based on how much material they were able to remove. So in third place was Sebastian Vavasori. He got to a mass reduction of 80.7%, and he used CATIA V5 and MSc Nastran. These are two different types of software, one actually being more of a CAD program, and then the second being a finite element analysis piece of software. Second place, we had Thomas Johansson. So he got to a mass reduction of 82%, and he used a software called Solid Thinking Inspired from HyperWorks. This is more of a generative design type of software. And then in first place, however, was M. Ari Kuniyawan, who got to a mass reduction of 83.4% using ANSYS MD. So again, this is a finite element analysis type software. So this is really sort of the skill of this designer setting up that simulation and reaching the most efficient and optimized solution. So what was cool about this is it hopefully gives you a sense that each of them used a different software, yet they all got to around 80% optimization. So there's a bunch of software out there. There's no right or wrong way to do this. But this GE bracket, this part, became kind of synonymous with how to showcase your software solution, how to show how quickly can you get to an optimization and what's the mass reduction, etc. So this part shows up all over the place. Most companies will use it as a demo piece, and you're going to see it all over the internet, especially if you search for generative design. So this is an analogy with, if you know 3D printing, again, this Rook piece became this generic sort of comparison part that all the different companies would be testing to compare technologies. So it has a little bit of history there, where the bracket is the comparison piece for design optimization software. Cool. So knowing that, we're going to jump into this great tutorial. This is a tutorial that's available online from Autodesk, and they use this GE bracket part as their test piece. So yeah, if you're looking for this, if you want to go through it in your own time a little bit more slowly, it's called Understanding Generative Design, available online for free. But we're going to fly through it, and hopefully you're able to follow and sort of get the gist of it in a sort of TLDR version. So let's walk through the 5 steps in the generative design process. The first step is creating preserved geometry. So here is our Fusion 360 workspace. The first thing we're going to do is load that original model in so we can draw over it. And we're going to define where we want to keep geometry. So we don't want it to be removed when we run our solutions. So the first geometry we want to keep are these mating holes. You perform this in a similar CAD function. You can draw some circles and extrude them. And then in the next step, you're going to create that hole. So these are all our preserved geometry. So if I flick back, we're keeping these 4 mating points, and we're also maintaining this pivot point. So there's our preserved geometry. And yeah, all of the sort of drawing tools are, your typical mechy CAD functions. So not particularly difficult to pick up if you're already a CAD user. The next thing you're going to do is create obstacle geometry. So you're going to outline where you don't want it to add material. So for this bracket, we get the sense it's going to mate down on a flat surface. So the first thing we draw is this flat area to say, don't put geometry here, because we don't want it to create, a collision, like something's gonna cause a problem when you try to bolt this thing down. And then we also want to make sure no material is in those holes. So we've built these cylinders through where we want those holes to be, through this mating point. And then the last most complex piece is that we don't want material throughout this pivot point. So they've created this big sort of thicker cylinder to keep that area clear. And then that's sort of it. So then we do a bit of cleanup and we're going to define our design space. So you sort of organize and assign geometry types to the bodies that you just created. So this is a little blurry, but here's your tree. And once you get to this stage, you have these sort of different things you can click on to indicate preserved geometry, obstacle geometry, and to also highlight the body that serves as your starting shape. So you can import that starting shape just to draw on top of it, and then you can kind of hide that and ignore it and not use it as you go through the solution process. So here we know we've clicked on preserve geometry, and then we're highlighting those smaller cylinders that we know we want to keep. And we would go through, do the same for obstacle geometry. And in this, now our starting shape has been hidden. So this is actually all the physical geometry information that's going to define where you can and can't put material. So now we kind of have the geometry constraints set up. You're also going to define loads and start to assign requirements of the solutions. So rules for the solutions must meet these criteria. So we're getting into the sort of where the skill comes in of how do you set up this design problem. Fortunately, this is a very nice example because, as I said, the loading conditions are really well understood. So we have these 4 loading conditions. We have a static vertical load, a static horizontal load, this angled load, and then there's a torsional load. So fairly easy to go and plug these in. So here we can highlight this internal surface, and we're going to apply this as that vertical load. And so now that we're assigning loads, this little dialog pops up and we can put in that 8,000 pound force. And you can sort of go through step by step and apply these 4 loads to your model. Then you get into assigning objectives. So here they make it really easy. A very common one is to try to minimize the mass. So you're trying to create a very lightweight structure. This is sometimes referred to as lightweighting. You also have the objective to maximize stiffness, and this dialog gives you the opportunity to apply a factor of safety. So this is great if, depending on like your confidence level in these loads, do you know that these are conservative loads? Are these sort of best guesses, but you're not sure? So you can increase the factor of safety there depending on how well you understand the problem. So here they've gone for a factor of safety of 2. Then you get into telling the system all the different ways you might manufacture this. So unrestricted can be clicked. That's when you're going to get all these like weird and wacky and wonderful geometries that may look very different to what you would have thought of using your own knowledge of manufacturing processes. And then explicitly, you can choose additive as an option. I'm not totally sure what the differences are between choosing unrestricted versus additive. I'm sure they're fairly similar because additive allows you to do a lot of very complex geometries. But the nice thing is you can start to add in some additional constraints. So depending on your knowledge of your additive system, maybe you want to minimize the overhang angle. Maybe there's a minimum wall thickness that you know your system can handle. So you can punch in those numbers there. Also fairly new to these systems, they're starting to build in more traditional manufacturing or subtractive manufacturing, which is cool. So you can also say, okay, well, I also could mill this. So we select that, and then you can say if you have a 3-axis mill or a 5-axis mill, you can put in some information about your minimum tool diameter and that sort of thing. So yeah, so you can punch in a design problem and you can actually look at a challenge like this. Well, should we mill the solution or should we 3D print the solution? And then last step is choosing your materials. So, if we have said we're going to look at additive and we're going to look at milling, then you may put in the typical materials you have at your availability to do milling in, and then you may also add materials that you might 3D print in. So built in, they have these materials profiles, and you can also create your own sort of custom profiles for different materials you might be working with. So that all gets plugged in, and that's sort of it. There you've kind of defined your problem. You have your geometric constraints, you have your loading considerations, you have your sort of goals, what do you want to optimize for, and then you have your manufacturing equipment and your materials constraints. So the last step is to go ahead and generate your design. So this is where it's probably going to look different depending on the software that you're using. Autodesk Fusion 360 make you pay for it at this point with cloud credits. They partner with Amazon Web Services so that now if you're working with Autodesk software and you're doing renderings, or you're doing, in this case, sort of computation around design solutions, they have this sort of unified way to pay through cloud credits. I think when you sign up, you kind of get 100, and then my understanding is they're about $1 per credit. So for this study, we may be faced with, okay, I know this is going to cost like $25. Do I want to move ahead? And obviously that's going to vary depending on the sort of complexity of the part you're designing and how much computation is going to go on. So this is the point, and I don't know how other software charge for it. There may be, you know, a subscription, you get unlimited. So there's definitely something to look into in terms of figuring out if you're going to be doing a lot of this, what software you're interested in. But assuming you think this is a great deal, and apparently we have like 500,000 cloud credits available, we're going to go ahead. So yeah, we're back at the screen. Here are our solutions. Again, there are these 4 views up here. I'm going to talk through a few of them. So this is a thumbnail view. Because we have asked it to sort by mass, and that was one of our goals, it's going to put the lightest one in sort of descending order down to the heaviest one. So you may just go ahead and look at the lightest one and be like, great, that's what I'm going to go with. But you may want to kind of look at some nearby solutions to decide which one you want to move forward with. So basically, once you generate designs, you kind of have 2 options. Either you're trying to pick one that you want to move forward with, or you're doing that inspection to maybe see, is there anything you want to tweak about how you set up that problem, and you could go back and reiterate. Or maybe you spit out all these solutions and you decide, okay, I think actually we're definitely going to use machining. So maybe you would do it again and look at machining options with a little bit more granularity to try and produce a few more there. The next view is a detailed view, very similar to thumbnail, except it just opens up and it shows us all the specific information for these different solutions. So, you know, we have the material, it's the titanium alloy. And then, yeah, as I said, you know, very small increases in mass, but generally moving in that direction. So then, you know, at some point, these are all very similar in terms of properties. There may just be like an aesthetic choice at some point where you're like, this one looks cooler than that. That's totally fair. You can also go into the scatter plot to sort of start filling out these trade-offs between different designs. So the scatter plot view allows you to select these 2 axes, and it's nice because these different solutions start to cluster. So you can kind of start to hone in on a specific cluster, and then if you click on a specific point, you're going to see which solution it's referring to in the details on the right there. So another thing you can kind of do is sort of start to drill down, and maybe you get down to 3 or 4 options. You can individually select those and then start to compare them on the same screen as well, which is pretty cool. So yeah, that was a run through of generative design. Again, I wanted to present it from more of a sort of mechie CAD perspective. Hopefully this feels not that different to maybe some FEA analysis you've tried, maybe some simulation software you've tried. So as with CAD, there's lots of different programs, there's lots of different ways to do generative design. And I think Autodesk have a really nice solution for people who are familiar with sort of a mechanical engineering type CAD program. So yeah, now I'm just going to talk about where additive manufacturing fits in, why we as Formlabs are interested in this as a topic, and sort of helping you understand the space. Basically, it's because these 2 technologies, as I say, work really well together. So these are really 2 technologies that go hand in hand, and partially that's because while I showed you there was that drop-down menu and various different manufacturing solutions you could pick, you know, that first bullet point that said unspecified, that was kind of like where these softwares started. So before you would run through this, it would spit out a bunch of designs and there wouldn't be sort of any manufacturing constraints attached to that. So in the early days, additive manufacturing was really one of the only ways to realize some of these sort of novel design solutions these softwares were spitting out. The second thing to consider is that a lot of companies, say you're GE and you're making that engine bracket, they might come to 3D printing and sort of say, okay, today we make this great machine bracket with milling. We're thinking about 3D printing it. And if you don't change the design, if you look at it purely on a sort of labor and materials cost, there may be no economic benefit to 3D printing that part. However, if you take that original bracket, traditionally manufactured, and then you apply, you know, like we saw with the design challenge, some optimization, so you get to 80% less mass, then that part may start to be cost competitive when you look at using 3D printing to manufacture it. Not only that, that sort of performance gain of reducing the weight may have other sort of cost benefits down the line, especially if, you know, this is a component going into an aircraft or, you know, a car or somewhere where it's very performance based. So these two technologies together can start to make additive look more economically viable for companies when you are maybe considering redesigning a part you traditionally make today. And then as a sort of happy coincidence, just these sorts of crazy organic structures tend to actually be easier to print with 3D printing than solid chunky things, because often they're sort of inherently self-supporting. So these sort of very complex organic, lots of trussing and lattice-based things are kind of like easier to print on 3D printing. That's why you'll see a lot of companies that are new to the space will be tending to print things that have a lot of latticing rather than solid chunky parts. So yeah, these outcomes just, again, play really nicely with this technology. A couple more things to be aware of. This might be the first time you're hearing these, but these are generally themes that come up when you're thinking about whether 3D printing makes sense. So additive manufacturing starts to be more cost competitive with higher part complexity. So in this graph, we see that sort of the cost of additive manufacturing is considered sort of relatively flat, despite this increasing product complexity. And that is not the case with traditional manufacturing, which is going to get more expensive when your part gets more complex. There's more sort of internal features and overhangs. So when your part's very complicated, 3D printing makes more economic sense. On the flip side, additive manufacturing is more cost competitive at lower production volumes. So I'm sure you've heard of sort of economics of scale. So when you are making a lot of something, the cost of traditional manufacture can start to come down because of the upfront tooling and these other sort of setup costs. Again, with the cost of additive manufacturing staying kind of flat, that means that it kind of is, it's good if you are doing a small run of something. So if you are interested in mass customization, or maybe you're a manufacturer and you have a minimum order quantity that's really high because of the cost of traditional manufacturing, using additive manufacturing could allow you to take on smaller jobs, be more flexible, be a little bit more exploratory with some new business that you might otherwise have typically turned away. So those are the good things. However, you know, pros and cons. So there are kind of 3 challenges that emerge that I would encourage you to kind of consider, at least be aware of at this stage. So the first is how to characterize novel materials. So while that tutorial looks very simple, you know, if you're going to machine it out of ABS plastic, that's a very well understood material, and you could grab that and put it up there. If you are working, say, with Formlabs materials, these are sort of specialty resins, and you know, these may be less plug and play. There may not be like a profile for these already in the software. So that's where you're going to need to maybe sort of you know, look to the technical data sheets from these companies, create custom materials profiles. You know, materials is really a booming space in additive. There's new materials all the time. So making sure that your simulation and your outcomes matches reality is also very important. So some companies who are using generative design and 3D printing may kind of have a feedback loop where they actually manufacture a part, and then they're going to probably measure the forces on it to help them refine their model and better get more predictable outcomes. Another thing to consider is this sort of non-traditional skill set may be needed when you want to model hard to define problems and solution spaces. So the example I gave, I have stressed multiple times. It was quite a straightforward example. It was the geometry was already known, the forces were already well understood and easily defined, and so it was quite easy to go through the process. But what if you're interested in something which is a little bit more tricky? Like the New Balance example I'm going to go into, they want to use runner performance data. So how can I take the pressure data from an individual's foot and use that to inform product design? That's not a plug and play problem, and they may need custom software to actually, and to do a lot of R&D to actually figure out how to take advantage of that input data. So with these design skills, it is always evolving. We kind of came from a world of sketch modeling and paper sketches. The next jump is moving to CAD design and digital design, which is, can kind of require a different skill set, or is something people need to work on to pick up. Then there's this further skill set of sort of simulation or finite element analysis, where you can kind of appreciate the designer just has a little bit of a different problem solving mentality, where the skill is really in understanding the sort of external circumstances around your part, and also having more of a brain where you can kind of think through the logic of what's going on, to look at the output and go back and sort of circle through the system and adjust part design as you go based on the simulation. So yeah, for me, generative design is sort of an extension of that sort of simulation-based thinking. And so the last thing is, while we've talked about part complexity is great for additive, where it is not great is if you are sort of on the back end. So if you're producing hundreds of custom parts, thinking through how are you going to track them through your production process? How are you going to make sure the specific part for this specific individual ships out to them? So when you're making generic parts, there are some things you kind of take for granted that go away when you're making more complicated or custom products. So this is an example from Arup. They're a sort of civil engineering company that do a lot of cool construction installations. And this was a project where they were working on a structure that had hundreds of unique joints. So these were already being made uniquely with sort of traditional machining. And then they looked at how could they optimize it using generative design and additive manufacturing. So here is the sort of joint in use, just so you get a sense. Each joint has both sort of is holding these in tension at different angles and at different positions. And then this was sort of gives you an impression of what the final structure would have looked like. And so I always think to the sort of construction company putting this together, how do you make sure when they get on site that they're going to put this together correctly when every single joint is unique? So I sort of compare it to like putting together a really complicated IKEA bookshelf where every single screw is different. And basically there are like 1,000 ways to put it together wrong. There's only one way to put it together right. So yeah, definitely these like really complicated, computationally designed buildings have very big implications on the construction side, and you kind of have to run with this much higher level of organization and part labeling and coordination. Cool. So now we're going to jump into a couple of examples. I know there have been some examples peppered through, but we're going to deep dive a little bit. So I want to talk to one Formlabs customer who this was sort of their first exploration into generative design, and they had some really great results. So hopefully this gives you a bit of motivation to maybe pick apart and try this process and just see what the value could be. So Wheel are a electric vehicle company. They specialize on personal mobility, and they're based in Japan. So their design challenge is how do they make a more portable electric vehicle? And the sort of design problem they hone in on is like, if you've ever seen someone trying to get a wheelchair in and out of a vehicle, it's pretty painful. And that sort of goes against the whole point of trying to help people get out in the world and enjoy their lives. So with their wheelchair, it's actually modular, it comes apart. And the part they focused in on was this sort of large metal piece that holds, I think, the electric battery. So here we have the original part design again. This was already a metal piece they were already manufacturing. You know, a lot of material there, so a lot of weight. And they worked with Autodesk Fusion to create this generatively designed version. So this is Yoshihiro Hirata, who's head of their vehicle development group. And he said they were able to lighten the frame alone by more than 40%, which he looks pretty excited about. So yeah, it's kind of crazy. This is a large metal piece, and you might be wondering how they use Formlabs technology. We do not have a metal printer. We make plastic materials, photopolymer resins. So I also want to touch on this sort of novel fabrication process that they use to realize this design. So because this part was so big, they had to split it into 4 pieces. So this is how the solution that came out of the Autodesk Fusion 360, they broke it into 4 sections so it would fit on their Form 2 build platform. Each of these pieces was printed on the Form 2 using our castable wax resin. So castable wax resin, if you don't know it, is typically used by jewelers. It is wax filled and it's designed to burn out cleanly. So you can print a part, pack it in investment, heat it so that it creates a negative, the material burns out and leaves a negative, and then you cast your metal into it. So it's typically marketed to jewelers for making engagement rings, casting precious metal, but it is also used in some engineering contexts, like it was here. So they took those 4 pieces, they assembled with sellotape, which again, I love the sort of, quick and dirty proof of concept of this, and seemed to work great. Then they did this elaborate sand casting process. So they're actually packing it in the sand, which has a binder in it. And then again, the whole thing's kind of baked. Our material is going to burn out, leave a negative, and that's where they were able to cast the metal into. So yeah, this is the final sort of proof of concept, the end of their project. They had this 40% lighter bracket on their chair, and that helps them definitely realize their goal of making this a much more portable mobility vehicle for someone. So yeah, they're working pretty hard now. Obviously that manufacturing process is pretty elaborate, but they've tried it, they're excited by the results, and now they're kind of working on how can they take what they learned and get to a solution that makes more sense for mass manufacture. So maybe that's not using this exact design, but maybe it's helping them reassess how they are machining their piece today. So yeah, super cool to see that going forward. All right, now I'll shift gears to a company that has more of a long-term vision for how they want to use this technology. We're going to talk about New Balance. So last year, New Balance announced the triple cell platform. So for them, triple cell is sort of their research effort that's at the forefront of this big industry shift. So they really think 3D printing is going to reshape how we all think about the design to manufacturing process for products. And I wanted to highlight this definition because they do talk about the manufacturing process. So this really is a story of 3D printing plus this generative design theme in the background. So here's the first R&D path they undertook, which was really focused on this midsole customizer. This was a collaboration between New Balance and Nervous System, who are a really incredible digital design consultancy doing really novel stuff in the generative design space. So they sort of approached them with a design problem. I'm going to start with this solution. So essentially they made this midsole customizer. You can see it has a very simple user interface here. They can go in and either, stand on a pressure pad or take some measurements for the runner and determine where their foot strike is. That's where sort of the majority of their weight falls as they run. they can input the sort of weight of the runner, and then it's going to automatically generate a unique midsole based on that performance data. So they're very excited about this as a foundation for a future of limitless on-demand customization. And yeah, this all started just as a sort of a collaboration. They came to Nervous System with the design challenge to improve the design of the midsoles to better adapt to the performance data from a runner. So this is not a closed problem. It's a very open problem, and it's not a problem that's really been solved before. So you can see here, these were some of the early 3D printed midsoles Nervous System developed, where on this foot, you can see there's a much tighter mesh on the sort of ball of the foot and the heel of the foot, whereas on the other foot, there's only really a tight mesh on the forefront. So this runner obviously has quite different running behavior on one foot versus the other. So this kind of shows you the level of customization that could lead to if they can take advantage of that knowledge. So yeah, they started with this performance data from the runner. Here is a plot of pressure data. They were able to kind of create a mesh from that, but they had to figure some stuff out. Like, so, okay, so we know where the runner puts most weight on their foot when they run, but how do you decide, what does that mean for how you design the product? So they actually had to do a lot of iteration to kind of take that data, create different meshes, test them with runners, and actually figure out what that means. So like with this data, what do you actually want the design to look like? So, you know, they've obviously determined that where the most pressure is falling, where the most force is applied, you want a tighter mesh. And that's what they've developed in this technology demo. So yeah, this midsole customizer was actually demoed at our first Digital Factory event. Yeah, I think it's something they're still working on, but this is from a couple of years ago now, so a little outdated, but very, very cool. And, you know, it does show you that if you want to do something very novel, you may need to develop your own software solution to get there. So the second R&D path they kind of went under in parallel was working with us. So they worked with Formlabs to develop rebound resin. So since then, they've actually launched 2 sneakers with rebound resin. So they actually used Formlabs material as end-use production parts. The most recent shoe they launched was the Fuel Cell Echo Triple, which came out in September of last year, where the black part, the sort of front of the shoe, was 3D printed. And the first shoe they came out with was a 1990 Sport Triple Cell, where the back of the shoe, the back of the heel was printed. So they're really kind of exploring in parallel, okay, how do we actually produce parts with 3D printing for end use? And for both of these, there are 500 pairs of shoes out in the world being used by runners and other people today. So the design challenge they approached us with was, could we match the properties of current performance midsoles to deliver the support and springiness athletes expect? So they sort of looked at our current portfolio of materials, they may have evaluated some of them, and there just wasn't something that would meet their needs. So they actually approached us on a consulting relationship to develop exactly the right material they were looking for. So in 2017, we started working together. New Balance and Formlabs announced an exclusive partnership. And together we created this proprietary new photopolymer resin that has much higher energy return, tear strength, elongation than any other Formlabs material. And also, I mean, these properties are very competitive with sort of all the 3D printing, midsole, shoe-based elastomer materials out there. So this is really at the cutting edge of materials development. But yeah, I mentioned, you know, already one of the things to consider with sort of mass customization projects is the sort of all the logistics around it. So not only did we develop a material with them, but we worked with them to create this seamless production workflow. So we also worked with them on logistics, on our supply chain. We provided on-site support. We have unique hardware setups and stuff at their factory in Lowell to make all of this possible. So yeah, that's kind of it. And I wanted to sort of highlight this because I think it's really cool how they have very distinctly followed these 2 parallel research paths. And, you know, I'm very excited for the convergence of them. but these are two technologies that have unique challenges in their own right. So while you may want to make, manufacture, mass customize something with 3D printing, I think this is a really smart approach to sort of break down the problem into smaller chunks. Cool. So a lot of information in here. This is a new topic for us, so I'm just going to circle back and sort of summarize what I hoped you would get out of the presentation today. So the first point is that if you know CAD, there isn't a huge learning curve to try generative design. I think it does have this reputation for being like super novel, like very cutting edge. However, I hope that by showing you the Fusion 360's tutorial, you kind of saw a very familiar workspace, and that this sort of well-defined problem is something you could definitely have a go at today. My second piece of advice is that if you are going to try a project, you should start with lightweighting. So taking a part you already make and figuring out how much mass can you take away while still getting the same performance. So lightweighting an existing part is a great starter project if you're exploring generative design. And lastly, I'd encourage you, if you do have a more ambitious end goal in mind, or you want to do something very disruptive versus what you do today, it would be smart to kind of break that long-term vision down into smaller R&D projects. Just because with that approach, you're going to be building up internal expertise, you're going to be able to show success at these different milestones. That's going to help you build traction in your business as well to really get where you want to be, because there's quite a lot to learn, and doing these things in parallel or doing these things in linear stages kind of sets you up for success. And finally, look to technology partners for expertise and support. So, these are very novel technologies, and I know both companies, whether you're working with Formlabs or you're working with your CAD provider, they have really great and intelligent sales engineers, applications engineers, people whose job it is to help you figure out how to leverage their technology that they're selling for your specific application. So you can do a lot of research, you can do your homework, but don't wait till you have everything figured out to start talking to these companies. Yeah, there's some great people there who are working with hundreds of different companies, asking themselves the same questions you might be asking yourselves. So yeah, definitely suggest, approaching a company to start talking about how their technology might work for you on the earlier side, and just, looking for very seriously impartial advice. Cool. So yeah, we talked a lot about generative design. Formlabs does not make generative design software, but we do work with a lot of our customers who are using it, and we thought it might be great to share this sort of high-level view of the space to make it a little bit more tangible for you. But if you do want to learn more about 3D printing, that's what we're great at, and that's what we know about. So since you made it to the end of the webinar, thank you so much for watching. I appreciate your attention and your time today. I wanted to highlight a new sample part. So our most recent engineering resin that we launched is called Tough 1500. It has a great balance of strength and springiness. And we have this sample part that you can request today to see it for yourself. If you're kind of new to 3D printing, we definitely recommend kind of seeing a part in your own hand to see the sort of quality, surface finish, and detail you can get from these materials. We also have many other materials if you have a specific application in mind, whether it's a high temperature application, we have a material for that. We also have elastic and other flexible materials that are more like a silicone or a rubber you can play around with, as well as a host of materials which are great for jigs and fixtures or low friction parts. Yeah, so lots to check out there, and hopefully you can find a part that speaks to you and speaks to the work that you're doing. And finally, if you're ready to get started and you don't need to see a part, you can also just reach out, like I said, to our fabulous sales team and start talking about your application today. All right, so thanks so much. That's everything from me. Encourage you to check out other webinars, and we hope to keep talking with you. Thanks for watching.